Okay, first, are there any pressing questions? If not, we are going to look at the problem sheet. But there should be some pressing questions. So let's go ahead with them first. Okay. It seems that nobody is willing to ask a question now. So let's start with the problems. And most of you have submitted already. So, and most of you have got at least parts of the problems right, if not all of them. So let me just take a look at the very first problem and just let's see how you would solve something like this. So there was a question in the discussion forum about what exactly does this thing mean? And I need to clarify that because although this is pretty standard notation, this may not have been taught to you before.
Hello,
Yeah.
sir.
Yeah.
Can I just ask one question regarding
Yeah.
the
Go ahead. Go ahead.
programming problem?
Yeah.
So,
Well, can we come to the problem? Okay, let's go ahead.
should we
Right.
use Fourier series to represent the square wave?
Well, that's one way. I'm not insisting that you use Fourier series or anything, but you can. In fact, the hint that did say that.
Okay, sir.
Right.
Yes, sir.
So
Thank you.
that's just up to you. You can do it in any other way you want as well. But the Fourier series is a good idea. So first of all, this was the problem. The question was find out the current through this 1 ohm. How much is this current? And many of you actually have done this right, but I would just like to point out a few things. First of all, what does this really mean? This 25 angle 0 degree amperes. This, of course, as you have all figured out, is the representation of the current in the complex format. When you say 25 angle 0, it really means mod of the I, or it seems like it means mod of the I is 25 amperes and its phase is 0 degrees. That means it should usually be I e to the I phi, or I mod I e to the I phi. That's what it looks like. And this is what the complex current should be. I of t should be e to the I omega t. Of course, you always have an e to the I omega t, which goes without saying. In all these problems, unless otherwise mentioned, you're going to assume that a sinusoidal input has been given. And of course, that's obvious because you are specifying the impedances of these inductors and capacitors, and they have definite fixed impedances only for a given frequency. So we are assuming that some particular frequency has been used for which the impedance are 3 ohms, 2 ohms, etc. Now, one very important point is that this 25 here really is not the magnitude of the complex number I here. The magnitude of the complex number I is actually 2 times 25. So this thing, as I've stated, is not quite accurate. So what you should really have is root 2 times this. Why? The important point is, unless otherwise stated, sizes of currents and voltages in AC is always quoted in RMS. Of course, if somebody says the current is 10 sine 10 omega t or 10t, something like that, that was there in another problem. There you are actually specifying the current I of t, and you can easily see that this 10 is really not the RMS value, is actually the amplitude. And the RMS value actually is 10 by root 2. If you wanted the RMS value in that problem. In that problem, you did not need the RMS value, but Unless otherwise mentioned, if you say it, when you say 220 volts is your mains, you do not mean 220 volts is the amplitude or the average value. There is no average value. The AC mains should have a zero average value. The 220 volts is the RMS value. That means the peak value of your mains voltage is 220 times root 2. And that's always the convention. So there's always an extra factor of root 2 to worry about. At the same time, you don't have to worry about it because when you say current is this much, you're also quoting the RMS value. When your answer says the current is something, you are really not giving the actual time dependent form with the amplitude and the phase and everything. You are actually giving giving it in this notation, the same notation as this one. So ultimately, this factor of root 2 is there in every one of the things, in the voltages, in all the currents and so on. So ultimately, whether you include the root 2 or not in your calculation, you will get the same result. In the sense that if you just say the I is 25, you just say I is 25 into the j omega t and do your calculation and miss out on the factor of root 2. That will not give you a wrong answer in the end as long as you don't imply this 25 is actually the amplitude. You understand from there that there's always an extra factor of root 2, which is common to all the quantities. But when I say all the quantities, I mean all voltages and currents here. Is this clear? So, for example, in the end of the calculation, what we are going to claim is that the current to this resistor is going to be something like 9 angle minus 97 degrees or something like that. That many amperes. That's the answer. Okay, after you do the calculation, this is what you're supposed to get. Now, does it mean that 9 is the amplitude of the current? The answer is no. The amplitude of the current is actually 9 root 2. 9 is the RMS value. So if you just start with 25, forget the root 2, you are going to end up with 9 here. Or actually 9.0 something. But you are going to get something close to 9. And 9 will be the right answer. So you don't really have to worry about the extra root. That's one point. Another point would be, do I need to write the answer in this form? Which is, of course, the polar form. Magnitude and the angle. The answer is no, you can use either polar or rectangular. Either one will work fine. Okay. So there may be multiple ways of writing the answer. You might even want to say that the actual current flowing is this times cosine omega t plus this angle. But when you do that, if you want to write the actual current flowing is this, then you have to remember that there's an extra root 2. Okay, any questions about this? Yes? Fine. So if everybody understands this, then we can move on. That's now the details of the calculation is sort of trivial because apart from the fact that you have complex numbers here, this is really nothing but the same calculation that you have done several times using resistors. The only thing I would like to point out is here the complex numbers are very easy to handle, but very often something which is very useful is something like this. For example, when I want to calculate Thevenin voltage here, that is, remember I want the current through the 1 ohm, and the rule for doing that is to treat 1 ohm as outside the black box. That is, the port should be this one. The one port in the one port network should be this one, to which you are connecting the 1 ohm. So the rest of the thing, all of this, is supposed to be inside your black box, which of course is a misnomer because you know precisely what is inside. When you say black box, you are supposed to not know what is inside. But here, of course, when you're doing the calculation, you know exactly what is inside. And now you want to calculate the open circuit voltage and the short circuit current, or find out the RThevenin in any other way. So basically, the first thing that you do is you realize that once you open this out, this becomes a very simple series parallel circuit. So what you want is how much current is flowing to this. Now here, you can actually find out the voltage across this, then divide by the impedance to find the current across this and so on. But the important point is you know that this is a current source which is driving 25 amperes in here. And now these are two parallel branches. This is one parallel branch. This is the other parallel branch. Remember, you have disconnected the 1 ohm, so there is no current flowing out through this. So this whole thing is one series combination, and these two are in parallel. So the important point would be the current which is flowing through this branch is an inverse ratio to the impedance of each of the parallel branches. That's all you really need. So basically, you start with 25 angle 0 degrees as the current going in, then you divide it in inverse ratio. Inverse ratio means it's proportional to the other one. So it's going to be minus j into 2 divided by the sum of the two, which is 5 plus 5, 9 plus 5 plus 3 minus 2, that's 1. 9 plus j6. So that's the current in this branch. And then you multiply it by 5 plus j5. That gives you the Thevenin voltage. So this is the quickest way of doing the thing. There are, of course, many other ways of calculating this. But if you do it this way, it's going to be fastest. So are there any questions about this? Did everybody understand what I've done here? This is elementary, of course. And I hope most of you have done it this way.
Question regarding the final answer.
What final answer?
Means the final answer, the current flowing through the 1 ohm resistor.
Yeah. Yeah.
I think it's pretty trivial, but I'm still asking because see, the current that is flowing through 1 ohm will have some phase difference with the actual current source, right?
Yeah, with the original current source, right? Yeah.
So that is understandable by checking the phase factor, whether it is negative or positive.
Yeah.
So yeah, my question is that any phase factor can always be, made positive and negative depending, because sine
By
and
adding
cosine are
360
harmonic.
degrees, right?
Yeah. So how do you understand whether it is leading or lagging, or
Okay,
is there any
that
range
actually is a
for?
very important question because basically, okay, I will now try to draw. So you must excuse me because I will now try to use my drawing skills here and try to draw a sine wave and a cosine wave, which is going to be horrible. But let's see. Okay, let's assume this is a sine wave, which of course it's not. And let's assume this is another. So this is, let's say this is your voltage, and now let's assume there's a current or whatever. Two different signals, V1 and I1, and I say X and Y. Let's just call them that. Let's call this X and this Y. So which one is leading, which one is lagging? Yeah. Which one is leading, X or Y? What would your point be? So in this figure, which one do you think is leading? Just tell me that.
Sir, Y is leading.
Okay, Y is leading because, for example, if you look at the peak, Y approaches, gets to a peak at a smaller time. So this is, of course, time. This is the signal, whatever the signal is. So Y gets to its peak before X does, right? Is it okay? Or Y gets to 0
Yes, sir.
before X does. In fact, Y gets to its trough before X does. So that's why you say Y is leading. But remember, Y's peak, this is a periodic function. So Y's peak is not just this one, it's also this one. Now, would you say Y gets to its peak here after X does? Because this is the peak of X, this is the peak of Y, right? So if you, instead of focusing on this peak of Y and this peak of X, if you are focused on this peak of Y and this peak of X, then it would look like Y gets to a peak a long time after X does, right? Yes? Any rebuttals to that? Anybody objecting to that statement? So what is it? Does Y lead or Y lag? Because if you were to focus on these two peaks, which seems like a natural thing to do, Y definitely leads. But if you were to focus on this peak and this one, then Y lags, right? But would anybody say Y lags in this case? If not, why not? What is the criterion? How do you decide? So just like this says 9 angle minus 97 degrees, but this could equally be written as 9 angle. Okay, now my pretty bad math skills comes into play. If it's at 100 degrees, it should be 260, so 263 degrees. Right? Are these two the same or different? 9 angle minus 97 and 9 angle 263?
Same.
Tell me. They're of course the same. So if you look at this, it's exactly the same thing that I've drawn here. If you look at this, it seems like my output current, the current to the 1 ohm, lags behind the input. If you look at this, it looks like it leads the input. But which is it? In this case, say if this angle were only 30 degrees here, it would be 330 degrees here. So if you say 30 degrees, Y leads the X by 30 degrees or lags behind X by 330 degrees? Which one do you use?
Sir, what if there is a range for theta that we should use, which
So
should
tell
not?
me what should be the obvious range here? In this case, what do you expect? Would anybody call? If you look at this signal, would you say Y leads or Y lags? Let's decide that first.
We would say that Y leads.
You will say Y leads, right? So you will look at 30 degrees rather than 330 degrees, despite the fact that both are mathematically correct, right? Both are mathematically the same thing. Saying Y leads by 30 degrees and lags by 330 degrees are exactly the same thing. Just like saying this is your answer is exactly, if it is the answer, then saying that this is your answer and saying this is your answer, exactly the same thing. You get my point? But then you have to make a decision. So what would be the natural thing to say? What kind of range would you use?
However, range from
However,
minus 180 to 180.
minus 180 to plus 180 would cover everything. And then again, by the way, this 30-degree lead could also be minus 150-degree lead lag. Or sorry, you were right. You're right. When you say minus 90 to plus minus 180 to plus 180, you mean minus would mean lag and plus would mean lead, right?
Yeah. Means the plus and
Yeah,
minus.
you're
has
not
been
going to
taken.
say lead is minus 180, but you're going to say if it's negative, it's a lag. If it's positive, it's lead.
Yeah.
Okay. And then, so the magnitude of that angle is confined to 180 degrees. You don't go beyond that. That's it. That's how you decide which one is leading, which one is lagging. If it lags by more than 180 degrees, then it's actually leading, or the other way around. And that's a natural convention we use. Given the fact that X and Y are both periodic signals, they will keep on repeating over and over again anyway. So there's no absolute way of saying which one comes first, which one comes afterwards. Remember, this lead and lag actually has this connotation that one of the signals is occurring before the other. That's why you say lead. But frankly, a proper sinusoidal signal should be there since time immemorial. If it's really a sinusoidal signal, then it should have no beginning or no end, right? Sine omega t keeps on oscillating from minus infinity in time to plus infinity in time. So one occurring after the other is actually a bit of an artificial concept. Here, what you do is look at the smallest gap between the two peaks. Instead of looking at this peak and this one, you look at this peak and this one. Or if you're looking at this peak, you will look at this one, not that one. Okay, the closer ones. So that is what gives you a 180 degree as an upper limit to the phase shift. If the shift is becoming more than 180 degrees, then you shift to another peak which is closer. Does this make sense? Okay, even if it does not, I will let you think about it, because it is an important point, but it's ultimately a convention. Okay. So then we come to question 2, where there is only one point to discuss, which is this. It's a very straightforward question where you have a Thevenin equivalent to whatever circuit you have, and the question was what should be the impedance connected here, which gives you the maximum power transfer. So condition for this, what is that? And somebody asked me, is power instantaneous power or average power? In AC circuits, unless otherwise mentioned, it's always instantaneous power. Okay, Soham is saying load resistance equal to Z Thevenin.
Sir,
Is there a dissenting opinion?
sir, it should be conjugate of Z Thevenin.
Yeah, this actually is wrong. So, of course, Z equal to Z Thevenin is a direct throwback to what you did in class 11, where the maximum power transfer told you that R equal to RS, right? In fact, we made this problem earlier where we had pure resistances, and there we had said R equal to R Thevenin. But Z equal to Z Thevenin does not work, actually. So the answer really is, for maximum power transfer, what you need this has, okay, so let's just try to show that. And for that, you don't really need a Thevenin equivalent. All you need is your V, you have Z0, and you have a Z. And you're asking how much is the maximum power, under what conditions maximum power transfer to Z, right? That's, after all, Thevenin theorem, what does it do? It changes your actual original complicated circuit into basically a circuit which is as simple as this one. So the current through the impedance Z is, of course, V by Z0 plus Z. The voltage across Z is Z times that. And the real question that you have now is, how much is the power? Again, by power, I don't mean instantaneous power, I mean average power. So how much is that? What is the formula for the instantaneous power? We worked it out last day. In the discussion class, we worked it out. The formula for average power flowing through a complex impedance in general.
VRMS into IRMS times cos delta phi, where delta phi is the phase difference between them.
So VRMS, IRMS, cos delta phi, that's actually true. That's the formula that you had learned in the previous class, in class 11, I guess. But we also gave you another formula, which is if you are using complex currents and voltages, which is what you should do, because after all, that's what makes the calculation a lot easier. In fact, that's what you have in your problem anyway. So what you really need to do is fall back on this. This is easier. Take the voltage, take the currents conjugate, or take the voltage conjugate, multiply it by the current, and take the real part at the end. Everybody agrees that these two things are the same. There was an extra half in the formula there, but that extra half only if you are using the actual complex voltages and currents. If you are using RMS values to denote the amplitude of voltage and current, then the extra half is taken care of, because the RMS will give you the extra 1 by root 2, 1 by root 2 to give you the half. Is this clear, or does anybody have any doubts about this? We worked this out the last year. Yeah. So,
Could you repeat once again what you said? The half factor.
about what?
How does it go away? Under what condition does the half factor is taken care of?
No, if you are using, when you say voltage and current, what are you really saying? Are you saying, after all, you're not giving the actual voltage and actual current, right? You can't. Actual voltage and actual current are real functions. So you're using sinusoids. Sinusoids, of course, are not, sorry, let me just back. Sinusoids are not complex exponentials, right? So what we are actually using here are complex versions. And when you say V is V0 e to the j omega t, do you mean the real voltage V of t is V0 cosine j omega t plus phi, or mod V0? You would, if you were to use the convention that your actual voltage is this. There is a real part of the voltage given. What you actually use in practice, at least when you specify your voltage and currents using the 25 angle 0 degree or whatever, some magnitude angle, whatever convention, remember what you are specifying is actually the RMS value. So your actual V of t will be root 2 times that. So there's an extra root 2 in your calculation anyway, which extra root 2 in V, extra root 2 in I. And that actually gets rid of the half. So if you're using RMS values for voltages and currents to give the phase and magnitude and phase, which is the convention anyway, there will be no extra half. So some books have the extra half, some books don't have the extra half. The extra half is basically, there are two possibilities. One is you say the actual voltage is real part of the complex voltage. This is what we have been using over the last few days to justify this. But in electrical industry, what you really use is this. Simply because when you say complex voltage, the amplitude that you give is really not the amplitude, it's the RMS value. So that's why you get an extra root 2 in your actual voltage formula. So you have a root 2 in the V, a root 2 in the I star, and they together give you an extra 2 which cancels the half. So whether this formula has a half in it or not depends on whether you are using the convention that the actual voltage is a real part of the complex voltage, or the convention that the actual voltage is root 2 times the real part of the complex voltage. So which is it? The answer is, if you specify that the actual voltage is this, for example, as I did in a later problem, then you have actually given the actual voltage. So there's no confusion. Then this 10 is really the amplitude. On the other hand, if you're quoting the voltage like this, or like the answer that was there, then this 25 here, for example, is the RMS value. That's always a convention under otherwise states. So then you have an extra into in your formula, which cancels out the half the answer. Root 2 cancels out half simply because there are two root 2's. So two of them cancel out the half. Is that okay? Yes? Now I'm beginning to worry whether I'm connected or not. Now the worry is deeper. It seems that I'm connected, but nobody seems to be responding.
Sir,
Yeah, go ahead.
sir,
Hello?
why you take I? Hello, sir.
Yeah, go ahead. I'm just
Sir,
getting
why?
some
Sir, why?
static from your end. Yeah, go ahead.
Sir, why you take
Yeah.
I of complex conjugate here? Why it is
So
not
complex
just
conjugate I.
only I?
Okay. Okay, so that's what we explained the last day, but let me just do it again. Ultimately, what we found out is this. The average power
Sir, I think your presentation is off.
sorry, I couldn't hear you. You think what?
Sir, we can't see your screen. Sir, we can't see
Yeah.
your screen.
Okay, so my presentation stopped. Yeah. You have to alert me if that happens. So when did that happen? Long time ago?
No, sir.
Okay, anyway, this is what we found out that is actually VRMS, IRMS. That's of course your class 12 result, cosine of delta phi. Okay. Now, as I said, your VR, okay, so what is V? V is actually, so the actual V of t. Sorry, it's the I phi one. I'm lapsing into the mathematician's version. It's J phi one. Is about J omega t. That is the V of, that's a complex V of t that we use. Okay, it might be useful to actually change the notation and put a tilde on top just to indicate that this is the complex value. Okay. Got it. Now, as I said earlier, you can deal with complex numbers perfectly well until it comes to a nonlinear operation. As long as you're dealing with linear operations in electrical circuits or linear operations, say, with electromagnetic waves in Maxwell's equations, it doesn't matter whether you start with complex numbers and keep on calculating with complex numbers till the very end. It's perfectly fine because you can take the real part at the very end and the answer will work out. But when you're dealing with a nonlinear operation like multiplying two such quantities or squaring one of them, in all such situations, you should actually take the real part first and then do the operation. And if I do that, that's how you end up with this answer. This is the actual correct value. But if you want to write everything in terms of the complex voltages and currents, now why would you want to do that? Simply because your calculation throughout has been in terms of the complex voltages and currents. So it's a bit of a bother to have to now suddenly switch to taking the real part and working with it. Okay, you understand that? So it would be nice if we could get a formula which uses directly the voltages and currents. Now, if I had multiplied V tilde t into I tilde t, note what you would get? You would get, first of all, phi 1 plus phi 2, not the phase difference, but the sum of the two phases. More importantly, you will end up with a very, very sharply time dependent factor with 2 j omega t. And taking the real part of that will not give you the right answer at all. On the other hand, if I took this, what will that give you? That will give you twice right? And if you take the real part of this, half of it, you actually get VRMS, IRMS, cosine phi 1 minus phi 2, which is actually the average power. Now, why do you conjugate the I and not the V? The answer is it doesn't matter. You could just as well take an V tilde's conjugate and I tilde and take the. And once again, do you put in a half here? The answer is that depends on whether you use the root 2 here or not. If you're just coding the VRMS, IRMS, you don't really put in the root 2, then the half cancels out anyway. Then you don't need the half. That's it. You start without the root 2's here, then you don't need a half here. That's it. So does that answer your question? The point is I already have a formula for the actual power. Okay, the actual average power we know is VRMS, IRMS cosine phi 1 minus phi 2. Okay. We want to be able to express this formula in terms of the complex voltage and complex current. Which, okay, strictly speaking, you don't, although this root 2 is correct, you don't mention the root. Okay. At least when you are using this V angle phi notation or I angle phi 1 notation, then you don't put in the extra root 2. The V here is actually the RMS value. Then this immediately gives you this calculation. Is it okay? So this is really a way of getting the right formula while using the complex exponentials. Does that make sense? Yes?
Yes, sir.
Okay. So it could be either V into I star or V star into I, because we are taking the real part in the end. After all, V into I star and V star into I are complex conjugates of each other. So when you're taking the real part in the end, they give you the same final answer. Okay. And the same final answer is actually the average value of the power, provided your V and I are, the complex V and I uses the RMS values. If they actually use the real amplitude, then you would have to put in a fixed factor of half. Okay. But that factor of half is really not important for our result here. What we really need is this. Remember, our final value then would be V0 by this is what V into I star would be, and you want to take the real part of that. I get, okay, let me just write this again because you may have forgotten this by now. But our voltage was V0 by Z plus Z0. Sorry, that was a current on the voltage. and the voltage was that times Z. That is the voltage across Z was that current times Z. So you have to multiply the complex conjugate of any one of them by the value of the other. So if you take I star and multiply by V, what you get is V0 by Z plus Z0 mod square. Because the complex conjugate of this quantity multiplied by this quantity is the mod square of that times Z, and you take the real part of that. And of course, this thing is already a real number. So this is what your power is going to be. Right? Now the question is, what should Z be that maximizes this quantity? Remember, V0 is a fixed quantity and Z0 is a fixed quantity. You're allowed to change Z. The question is, how should you change Z to maximize this quantity? Or how should you change Z to minimize this quantity? And the answer is not Z equal to Z0. The answer would have been Z equal to Z0 if instead of real Z you had Z here and this Z were a real number. Well, let's think in terms of complex numbers. Z equal or real parts and imaginary parts of this. Let's write Z equal to X plus Iy and Z0 as X0 plus Iy0. So this quantity simply becomes and now you are asking what will give you a maximum value for this quantity. Sorry, minimum value for this quantity. This, remember, is in the denominator. So maximum power transfer means minimum possible value for this quantity. And X and Y, the real and imaginary parts of Z, can be chosen independently. So here, this is a problem of minimization in two variables, which of course is a bit more advanced than minimization in only one variable, which you have done in class 12. But you have already done this minimization in multiple variables before, I am pretty sure, in one of these first 2 years here. But in this case, you don't even need to worry about complicated things like multivariable calculus. One very easy way to see what's going to happen is, let's first fix X for a given X. What value of Y will minimize this expression?
Y plus Y not equal to 0 means
Right? Y plus Y not equal to 0 will of course minimize this expression for any fixed X. Right? Give me any fixed value of X. You want to get the minimum, then Y plus Y0 has to be 0, because this thing after all is a perfect square of real numbers, and so it's never negative. So what you want to do is get rid of this. So what you demand is Y equal to minus Y0. This has to be the case. And then you want to choose your X such that this minimizes this expression. Now this expression, well, you can use calculus for this, you can use algebra for this, or you can simply use the fact that this expression is exactly what you had in the maximum power transfer with resistances, right? Just hold on. Risha, class achi, class pade kobi? 11টা pade. So we know the answer for this. So this has to be X equal to X. Right? Well, if you don't know the answer for this, you can work it out by using either algebra or calculus. I would prefer algebra, but calculus is fine. But all of you have done this, right? Sometime or the other. So the question really becomes the answer really becomes this. In order that the power transfer be maximum, what you need is the real part of Z must be equal to the real part of Z0. But the imaginary part of Z has to be negative of the imaginary part of Z0. That is, Z has to be Z0's conjugate. That's your answer. So those of you who use Z equal to Z0 to find out the answer, you did it wrong, but that's fine. That's something you use a bit of knowledge which you had somewhere else and directly applied here without verifying that it can be done. There's nothing wrong with that. You can try it, but sometimes this kind of lateral movement of knowledge from one one thing to another, or sometimes gives you trouble. And this is one example. So Z is actually Z0 star, and the final result would actually be much simple. Final value for the power would end up being a pretty nice, simple answer, simple number, not a complicated one which you would get if Z were equal to Z0 star. Z were equal to Z0. Okay. Any questions about this?
Sir,
Yeah.
sir, when we take the Cartesian form of complex number, let's say b equal to a plus jb and I equal to c plus jd, then what
Yeah.
will be the power here?
Over here. You mean V equal to, you mean V, right?
Yes, sir. b equal to a
X
plus
plus
jb.
I equal to C plus JD, right?
Yes.
And you are assuming, and these are RMS values, right? So then this V into I star is A plus JB to C plus JD, right? And you're, sorry, C minus JD, and you're only interested in the real part. So real part of this, that comes from multiplying the real parts and the purely imaginary parts. So AC plus BD. That's a simple calculation, although this calculation is much easier to do in the polar form. Is that okay? You actually carried out this multiplication, you will get AC plus BD for the real part. You would also get minus AD plus BC for the imaginary part, but the imaginary part doesn't come into the final answer. The final answer is just the real part. Is that okay?
Okay, sir.
Sorry, I didn't get you. You say yes or no?
Yes, sir.
Okay, then we had a rather simple Laplace transform problem.
Sir.
And essentially, the Laplace transform problem boils down to it's a CR circuit with rather simple values. So ultimately, it boils down to this equation. This is the ODE that you have. Then you need to solve it using Laplace transforms, and the solution is really rather simple. You take the Laplace transform of both sides. So if Laplace transform of Q is LQ, then Laplace transform of dq dt is actually S times LQ at S minus Q at 0. So you just get S times LQ at S minus Q at 0, but Q at 0 is 0 for this problem, because the initial value has been given to be 0, plus LQ. Okay, you can try using some other notation, like say Q tilde is you're writing LQ. So it might be less cumbersome to write this. S times Q tilde of S minus Q of 0, of course, but Q of 0 is 0, so it's not there. Plus Q tilde of S is 10 times the Laplace transform of sine 10t, and that's 10 times 10 by S square plus 10 square. So Q tilde simply becomes 100 by S square plus 100 into S plus 1. And then you simply divide that up into partial fractions like this. I'm sure your class 11 calculus must have taught you this. How to do partial fractions for doing integrations. You find out ABC values, then it becomes a simple task of just looking up the what do you call it? Looking up the inverse Laplace transform table to find out the answer. The great thing about using Laplace transforms is that it gives you the full answer, including the initial condition. So you get the complete answer, not just the steady state value or something. Any questions about this, or can I move on to the next point? Again, no questions. Wait. I'll just say whether I can move on because I want to know whether I'm still being heard.
Yes, sir.
Okay, I'm being heard. Okay. The next problem after this is the only one here in this problem sheet, which is actually a complicated problem. Complicated in the sense that it's difficult to set up the differential equation for this one. Take some steps. Okay, I want to check what people have done in the submissions, if they have done it at all, before discussing this. So I'm going to keep this for Thursday, because I want to see what people have done. And in the light of that, I want to discuss this particular problem, the one in which you had this RLRC combination, and you had to write down a differential equation for this. The reason why I want to see what you have done is not because of anything else, but simply because there are several ways of doing it. And if people have already found out the easiest way, then I don't really have to waste much time talking about it. If not, I will talk about an easier way. So let's do that on Thursday. The extra element theorem is a trivial problem. Anyway, I'm going to give the solution soon. So you will see the solution to that. But after that, we had this lead-lag network thing. But here I have a question for you. At least for the people who have watched the video. I have forgotten, because this was 1 year ago, whether in the video I discussed anything about oscillations or oscillators. Can anybody tell me that? That is, what are lead-lag networks good for?
Yes, sir, you discussed about that lead lag networks will be beneficial when we are discussing about oscillator.
But did I tell you anything about that? Anything about oscillators? Or just mention that it's going to be useful for oscillators?
And not much, sir. You just mentioned and give some hints about it, not anything extra about it.
Okay. Anyway, we are going to discuss oscillators in a big way later on anyway. And we have to. So there's not much point in talking about that a lot now. But I hope everybody got this point about how would you identify this result as a lead-lag network without actually doing the calculation. By doing the calculation, you can of course do that, find out the answer, right? So this is RC, and then you have CR. That was the original lead-lag network where you used equal C's and equal R's. But anyway, here we used R1, C1, T2, R2. So you had a VI here, some sinusoidal voltage going in and some sinusoidal voltage coming out here. Okay, so this is the VO, the output voltage. And the point I tried to make in that video, which is a very important point, is that you can make out whether the output is going to lead or lag without going through the full calculation. And the answer to that, and the way in which you do that is realize that if you have this, so this is what is called an RC circuit or CR circuit. What is this called? What is this circuit called? CR or RC?
RC.
What is this circuit
Won't
called?
won't that depend upon where we are taking the voltage output?
Exactly. So when you write it like this, so let's put in this. Now what is this called? This one? It's a convention, of course, it's the same circuit. But if this is the way you take the output, say for this one, what is this really called? RC or CR?
Yeah, this will be RC.
Okay, it's just a convention, right? So you have to settle on something. Will this be RC or will this be RC? And what is this? Okay, anyway, the name doesn't really matter. What matters much more is here. Will you expect the output to lead or lag the input? So let's take a look at this circuit R here and C here. And suppose this is a current. I'm using the phasor diagram notation. So the voltage to the resistance should be in the same direction. Voltage to the capacitor, which way will it be? In the phasor diagram? I'm assuming everybody here knows phasor diagrams, right? So we also discussed what they mean in terms of complex numbers last day. So what was the phasor diagram for VCB? Which way will it point?
So
It will be
perpendicular
pointing
to
downwards.
pointing downwards.
Yeah, it will be perpendicular and pointing downwards. This is VC. Right, 90-degree negative phase. That's it. Compared to the current. And this will be the input voltage then. So VC is of course our output voltage for this. So compared to the input voltage, which is like this, VC is like this. So is VC behind VI or above or ahead of VI? In other words, if the phase difference between VC and VI is VC below VI in phase or above? In order to go from VI to VC's direction, do you have to go through a positive angle or a negative angle?
Positive angle.
VC is here, right? Actually. To go from VI to VC, from VI to VC, from input to output. Which way do you have to go? You can, of course, go through a positive angle like this. Remember, counterclockwise angles are positive. Right? In a diagram like this. Or you could go this way. Which one would you actually say is the phase angle? The smaller one or the larger one?
The smaller one.
Yeah, that's exactly this 180-degree thing, right? You have to keep it below 180 degrees so that you can unambiguously say lead or lag. You could, of course, say VC lags behind. This is lag, right? It's behind. VC, so if you think of the whole thing spinning around, so this whole thing is spinning, this is going round, this is also going round. Whenever any one of these vectors go to the horizontal axis, they reach a maximum. So which one will reach a maximum first, VI or VC? Imagine the whole picture is spinning like this and they have to go through the horizontal. The VI will go through the maximum first, right? But it will come here. At that point, VC is here. Only after VI has crossed the maximum will VC go through its maximum. Of course, you might say VC has actually gone through a maximum long time before VI got there, but that would be looking at the other peak, as in the picture that we drew at the very beginning. So here, VC lags behind VI. That's a conventional statement, and VR leads. So when you're taking the voltage across the capacitor, it lags. When you're taking the voltage across the resistance, it leads in terms of the VI. So if you look at this particular circuit, now this is not a simple RC or CR circuit. It's more complicated than that. But I explained this in the video, but maybe it's important to repeat that. With the capacitance, you all know that the impedance depends on the frequency. When the frequency goes down, the impedance of a capacitor goes up. Now, here you have a series combination and a parallel combination. So when the frequency is very, very low, the impedance of the capacitor is, or both capacitors are huge. So when you have a series combination between two impedances, which one dominates, the smaller one or the bigger one?
Bigger one.
And the total impedance is like the bigger one, right? So for very low frequencies, this part will be like what? Capacitor or inductor? Or capacitor or resistor? Sorry.
Capacitor.
Capacitor. And this part will be like?
Resistor.
Right. So here it's like you're taking the output across a resistor in a resistor capacitor combination. So here the output will lead for low frequencies. If on the other hand you go to very high frequencies, the both capacitors will have rather low impedances. But now this combination will look like the resistance, and this one will look like the capacitance. So now you're taking the output. Remember, the output is being taken at the same place, but for low frequencies, it was as if you were taking the output across R2, right? Because the parallel, very huge impedance can be ignored. If you have a huge impedance in parallel, you can just ignore it. If you have a huge impedance in series, you have to take that one. And at high frequencies, on the other hand, it's like you are taking the output across a capacitance of a capacitor RLSA combination. So at high frequencies, the output will lag. So the important thing here for this particular circuit is, as you change your frequency from low to high, your leading output, before the output was leading for low frequencies, will lag for high frequencies. Somewhere in between, there will be exactly one frequency at which there will be neither lead nor lag. Okay, and that is exactly what you are really aiming for. This is really why this circuit is at all any good. Now, I'm not going to discuss in detail the calculation for this particular circuit because that's sort of trivial, no real issues here at all. Okay, it's really a straightforward calculation. But I would like to talk a bit about the oscillator thing. So what exactly is an oscillator? Can anybody tell me that? You may not have studied oscillators before. You may have or may not have. But at least you should have an idea of what an oscillator is or what it does.
So it oscillates electrical and magnetic energy.
Could you just repeat that? It was too low, or be a bit louder.
So it oscillates electrical and magnetic energy.
Electrical and magnetic. So basically, what you want is an electrical signal to come out. Magnetic may or may not be even involved. Okay. The kind of oscillators, maybe you're talking the LC oscillator, and of course you have magnetic and electric. Sorry, I was cut off for some time. So could anybody just tell me when was it that you last heard me?
Yes, sir, we can hear you now.
No, you can hear me now. But what did you last hear? That's what I'm really asking. Okay, anyway, what I was saying was an oscillator, as far as we are concerned, is something which produces an output signal, a sinusoidal output signal, or a spiral wave or some other periodic signal, without an input signal. That is not a violation of the conservation of energy, for the simple reason that energy conservation would have been violated if you had output power without any input. Here, your circuit would have some kind of power supply, let's say a battery. So the power supply would be supplying the power. The oscillator would essentially be converting this DC supply into an AC signal. So it's not as if you are getting power out of nothing. You are getting output power, but you are actually converting one kind of power, static DC power, or not static, but DC power, to AC power in that sense. Okay. Now, the way in which oscillators work, we are going to talk about that in detail later. But a very easy way to think about an oscillator would be something like this. An oscillator is a box with some input and A times, so whatever VI you give, A times VI goes an output. Now, if you can manage to feed a fraction of the input back to the output, so beta VI comes back, let's say, then what happens? This is, remember, is an amplifier, not an oscillator. This is just an ordinary amplifier which takes an input, produces an output. But if you fed back the output, a part of it back to the input, then what can happen? In principle, what can happen is this. The fed back input can actually produce another output that will come back again, that will add up, that will add up, that will add up, and ultimately you end up with an output without an input. The output will keep on growing without an input. Now you might say, how is that possible? After all, for this to happen, at least you need an input to begin the whole thing, right? You have a VI, then only you have an AVI. Then you can bring its feedback back, a part of it back. Now the answer to that is all electronic circuits do have signals even when they are not connected to a source, simply because there are thermal fluctuations, random motions of the electrons inside the circuit, which always behaves like a tiny input signal, but it's usually too tiny to bother you. Sometimes it becomes important to bother you. If you amplify it too much, you would hear the hiss, the annoying sound that you get. That's the thermal noise being amplified too much so that you can hear it over on your mic, on your speakers. But basically you have thermal noise which is tiny. But if you can manage to amplify the thermal noise, but more importantly, bring it back again so that it can feed itself, then the output is going to keep on growing, and it's going to grow without bound. And you are going to get an output without any source. Okay, that's how an oscillator really works. But there's one important point here, which is very, very important. There are two important points. One is the part which is fed back. Let's say a fraction of this output is fed back. So the VI went as AVI, a fraction beta, not beta VI, beta VO, sorry, is fed back. So what is going back again is beta A. So if beta A is greater than 1, only then is the output going to feed itself and grow. Is it okay? If beta A is less than 1, then what comes back becomes smaller and smaller and smaller. You don't really add up. It doesn't really add up to anything, or it just dies out because you started with a very small amount, so it doesn't really grow too much. But if, for example, beta A is 2, then you send in a very tiny signal. After it goes back once, it becomes double of itself. Then it goes back again, it becomes double of itself, and you get exponential growth. It's after going through the circuit several times, it becomes huge. Now, that's one part. The other part is this beta A has to be exactly real. That is, imaginary part of beta A has to be exactly 0. In other words, the output has to be fed back to the input, but it has to be exactly in phase with the input. If it is not in phase with the input, then it's ultimately going to destroy the input. This is basically destructive interference, which happens in optics, the same thing. It has to be exactly in phase. And that is where this network comes in. If you have an amplifier with the output, that's one way of making an oscillator out of an amplifier. You take an amplifier, take the output of that, and put it through this lead lag network. And then the output of the lead lag network, feed it back to the input. The point is, thermal noise has all kinds of frequencies, but only for one such frequency will the input be exactly in phase with the output. Okay, input of to this will be exactly in phase to the output, and only for that frequency will you actually get an oscillation. Otherwise, you will not. Which is great, because you don't really want thermal noise to be amplified and you get a huge number of different frequencies. You want one particular frequency. Okay, so this is how a very simple oscillator can be built. And this oscillator has a name. It's called a Wien bridge oscillator. You will meet the Wien bridge in the next lecture soon, when we talk about AC bridges. You may not be able to recognize why this is called a Wien bridge oscillator at this point, because we have not drawn the full circuit. We have just drawn the amplifier with a box. But when we talk about this circuit later, when you draw the amplifier fully, you will then recognize why it's called a Wien bridge oscillator. The Wien bridge was a circuit which was known long before this oscillator was known. Now, I'm assuming, well, I am deliberately sort of skipping ahead of some details, except for one thing. I will just want to talk about one interesting fact about this. We are going to come back to this later when we talk about oscillators in some detail. In this oscillator, basically what happens, okay, I'm just going to give you the answer to this in a way, without giving you the details. The gain of this amplifier is given by something like this, 1 plus R2 by R1, where R2 and R1 are two resistances. You need to know only this much for the time being. Why is this 1 plus R2 by R1, etc.? We are going to talk about in some detail later. Well, R2 and R1 are just two resistances. That's all you really need to know. The important point here is this. If this fraction beta A were more than 1, this is A that I'm talking about. If beta A were more than 1, then the input will, a tiny input gets amplified to A times that, comes back as beta A times that, so comes back bigger, right? Then the output becomes even bigger, then it becomes even bigger, then it becomes even bigger, and you get a huge output. Of course, a real amplifier will never give a huge output. What will happen is the output will simply get distorted because of nonlinearity. There may be an upper limit to how much output that it can be. Then it will just go and stop there. So you will get a flat peak. The output will look somewhat like this, instead of a sinusoid, which you really want. Is this clear to everybody? If the output kept on growing, then in principle it would look like it will go to infinity, but it can't. Your circuit can't give you more than a particular value, so it will just give you something like this, which will be a periodic oscillation, but not a sinusoidal oscillation. If you want a sinusoidal oscillation, you want to sort of ensure that beta A actually does not become bigger than 1. You want beta A to be exactly equal to 1, so that it just self-sustains, does not grow. But on the other hand, if beta A is 1 to begin with, then you have the trouble that the signal will self-sustain, but at whatever tiny initial value you had. Remember, your signal initially was made out of thermal noise, and thermal noise is tiny. If you just manage to keep it going as it stands without amplifying it, then what you're going to get is almost nothing, a very tiny value. So the question that I have for you is this. How would you think that you solve this problem? You want to make the oscillations grow, but you don't want to make them grow without bound. So what would you do? I'm asking for ideas. Any idea would work. So the idea could be crazy, but just what do you think you should do? Has everybody understood the point? If you have beta A equal to 1, you have self-sustained oscillations. That's fine. Except that you can't have beta A equal to 1, because if you have that, then your oscillations would be self-sustained at a very tiny value. You want beta A more than 1. But if you have more than 1, then it becomes way too big and gives you something like this, not what you want. So how could you possibly handle a situation like this? Okay, at least if you don't say something, I'm again getting worried that nobody is listening to me.
By adding a time-dependent resistor.
Time dependent, right? So you mean that might work, except that it would have to change with time very rapidly, right? You mean when the output goes towards the peak, the resistance will become big.
Yes.
Then it will have to change very rapidly with time. And having a time dependent resistor, is that an easy thing? Okay, let
No.
me just give you a hint. Okay, hello. Yeah, you were saying something? Hello? I've actually given you the form of the gain. So let me just give you a hint. If you could have a situation where A is large for low amplitudes, but once the amplitude becomes big, A becomes small. Then somewhere in between, so then beta A could be big for small amplitudes and become smaller for large amplitudes, so that once the amplitude becomes big enough, beta A could be equal to 1. That's one way. That is, you can try to create an amplitude which depends on an gain factor which depends on how big your signal is. Okay, so amplifier which does not amplify all signals equally well, it amplifies small signals by a large amount, but does not amplify large signals by the same large amount. It amplifies large signals less. If you could arrange that, that would be nice. So I've given you an answer, given you the form for the A. Can anybody guess how you could possibly ensure this thing that I wanted? You want A to be large when the amplitude is small, and you want the gain to be small when the amplitude is large. The formula is given, 1 plus R2 by R1, resistance ratio. So of course, if you want that, you want the resistance to depend on the amplitude somehow. Can anybody think of a simple way of doing that? Does the resistance of a circuit depend on how much the signal is? When you say resistance is say 1 kilo ohm, is it 1 kilo ohm for a 1 milliampere current or a 1 ampere current? Or does it not matter? Yes? I don't expect you to know the answer, but you should be able to guess. From this fact, the resistance, does that depend on signal size or does it not depend on signal size? Yes? The 1 kilo ohm resistor, 1 kilo ohm resistor for all currents. If I drive a huge current through that, through a signal, through a resistor, what happens to it?
So due to heating, maybe the resistance can increase.
Due to, sorry, could you be louder? Louder?
Due to heating.
Exactly. So if you have a amplitude, then due to heating, the resistance may increase. Of course, this is a resistance ratio of R2 by R1. So if they were both made with the same material, then of course they would heat up equally and R2 by R1 will be the same. Doesn't matter because the resistance ratio will not change that. However, if you made R2 with an ordinary resistance which does not heat up too much, and R1 with something which heats up a lot and whose resistance changes a lot, then this can work, right? So can you think of something for which the resistance changes a lot with the amount of current flowing through it? Some simple device which everybody has seen, everybody has used, by the way, for which the resistance depends drastically on the current through it. Simply because it heats up a lot. When it heats up so much that it starts to glow. What is it that I'm talking about?
A fuse?
A fuse. A fuse. Is that what you're saying? Fuse.
Yes, sir.
Yeah, but a fuse would the fuse's job is to essentially melt, right? When you send too much current. But I'm surprised. I gave away the answer, right? I said it becomes so hot that it starts to glow.
Using diodes?
Using diodes. Well, diodes, frankly.
Yeah, are you talking about tungsten bulb?
Yeah, I'm talking about a bulb, an incandescent bulb, right? Not necessarily a tungsten bulb, but anyway, any kind of bulb, basically. Okay, diodes, of course, would work, but they are way too complicated things. Why don't you think of simple things? Simple things are bulbs. Bulbs heat up a lot when you send in current through them, and in fact, the resistance changes drastically. Okay. So the person to whom this idea came first, he actually spent his entire PhD, almost his entire PhD duration in MIT, checking out the variation of resistance of different bulbs that were commercially available in the market. That essentially was what his PhD was about. How does the resistance of different bulbs change with temperature? He spent almost his entire PhD doing that. And right after his PhD was completed, what he did was he found out during his PhD exactly which one of the bulbs that are available in the market would do a good job for this particular purpose. Remember, those were the days when people used big bulbs, not our semiconductor diodes and triodes and transistors, but big diode bulbs or triode bulbs, which had a lot of current flowing through the circuit in building amplifiers. So what this person did was figure out exactly which bulb would work best for this, to build this kind of oscillator. And once his PhD was over, he teamed up with a friend and, as people did in those days, opened up a company in the friend's garage. And what they did was build these oscillators, and that's how they started their company. So the company started with a very basic electronics problem. You want to get a gain which changes with amplitude, and how do you ensure that? You ensure that by ensuring the resistance changes. That's it. Now this friend was called Packard, and this PhD student was called Hewlett. So you know what I'm talking about. This is the way in which the HP company was formed. Okay. HP started out making Wien-Dietrich oscillators. Sorry, I wrote a lecture. What is that? HP's first product was this, and it was a product which came directly out of Hewlett's PhD thesis. All he did in his PhD was essentially measure resistance variations with temperature, and once he did that, he could actually build a proper working circuit. And that's how one of the largest companies in the world started, just by this kind of simple electronics. Okay, that's all I really wanted to say today. It's sort of an advertisement for why people study electronics anyway. But it's quite nice and interesting to learn about these things. Okay, let me just move on to the last question here. There were 4 circuits, and we asked what kind of circuits they were. What I'm going to do is all of you can definitely do the algebra. And frankly, there's nothing very interesting in the algebra. But let me try to see whether we can understand the behavior of these circuits without actually calculating the whole thing out. The question was something like this. Is this circuit going to be a low pass filter or a high pass filter or a band pass filter or a band stop filter? Low pass, of course, means low frequencies are passed more, high frequencies are damped or taken out. High pass means high frequencies pass through, that is, the output has more of the high frequencies than the low frequencies in the input. And band pass means a range of frequencies in somewhere in the middle, they get passed. So that's like that's essentially a resonance circuit. And band stop would mean a situation like this, where VO by VI versus frequency would look like this. That is, a range of frequencies in the middle, a band of frequencies is stopped. Either stopped completely or lower drastically compared to others. So this is a band stop. A low pass looks like this, the same graph. For the low pass, the same graph looks like this. For high pass, it looks like this. For band pass, it would look like this. So here, what we are interested in is what kind of frequency dependence the circuit will have. The details, of course, for that you have to calculate the whole thing. But here, for example, at very low frequencies, the capacitors will behave like what? Remember, capacitor impedance is 1 by j omega c, right? For very low frequencies, what happens to capacitor? Large impedance or
large impedance.
So if it is a large impedance, yes. I think I'm getting a lot of feedback from your mic. Anyway, it's not. So if it's a large impedance, what happens to the output? When for omega much very small omega, let's say. So almost no current flows in the circuit, and then no drop across the resistance. That means whatever is the input that occurs across the output. That may be a bit difficult to sort of intuitively understand sometimes. How can low current be large voltage? But remember, current is related to voltage drop. So low current through R means low voltage drop across R, which means almost the entire VI will go across to VO. So basically it starts out large. And when frequency is very high, then impedance becomes very small for the capacitor. So very little of this whatever voltage is here. First of all, even here, this is a very low impedance, so almost all the voltage dropped across the resistance, none across this. And even whatever is dropped here, that gets divided between R and C, and there also most of it gets dropped across R and less. So this essentially will be a low pass. You can understand that without doing the calculation. But can anybody tell me what difference will this have compared to just a single RC circuit? we just had one block, if we did not have two. Then also you would have this kind of behavior, right? So I'm just asking you to guess. If I were to draw the output versus input for this circuit using red, will it look like this? Or will it look like this compared to the other one? So will it look like this one or this one? One or two. Where the black line is for the two RCs. That is, black line is for what we originally had. Compared to that, will one RC give you this graph or this graph? Is the question clear? If the question isn't clear, please ask that. So yes, sir, I'm assuming when you say yes, sir, you are saying question is clear. So now, answer. If you drew the VO by VI versus frequency curve for that two cell system that we already had in black, and that for the one cell system in red, which one of the two red graphs, the graph labeled 1 or 2, would be the correct graph? Yes? In other words, do you expect the output to fall more sharply for a single RC or more sharply for a double RC?
So it should fall more sharply for a double RC.
So then the correct answer will be one or two.
One.
Remember the red one is for the single RC and the black one is for the double RC.
Oh, then two.
Yeah, two would be the correct answer. So these are things you should be able to figure out on your own. Yeah, without doing, when I say on your own, I don't mean without my help. I mean without having to use a lot of algebra. Okay. So now that I'm going to talk about this one, RC. So, yeah, for low frequencies, would you expect VO to be large or small? So think of it in steps. When the frequency is low, then this capacitor is almost a huge impedance, right? So it's almost as if it's not there. Then you basically have this resistance, this capacitance, and this resistance. And this capacitance is huge. So will the output be large or small?
Output should be small.
Right, the output should be small. For low frequency, it should be small. For high frequencies, what should it be? Very high frequencies? Now, by the way, the others who are listening in, you don't understand why it should be small, please speak up. Later on, when I take a Viva, I'm going to assume that all of you have understood whatever is being said here. Okay, low frequency is small. I'm assuming everybody has understood because nobody is saying no. High frequency is what will happen.
So at high frequency, the output should more drop across the first R that we have. So across the second R, the output should be small again.
Good point. Actually, you could even just say that at high frequencies, this C is almost like a short. So that's essentially shorts out this whole combination. So basically, it's like R with a very small impedance, and that's what you're getting the output. So you're again going to get a small value. So basically, you expect something like this. So here, so basically, all you need to do is take a look at the limiting values, and that should tell you roughly what the behavior will be like. Here is going to be a band pass, which of course you can verify by doing the full calculation and figuring out that this is really the resonant circuit formula that you're going to end up with. Ultimately, you're going to get the formula for a resonant circuit here. But even without doing the calculation, if you just look at low frequency behavior and high frequency behavior, you should be able to guess what each one of these will be the correct one. What is very important is having this, whenever you're doing a complicated calculation, you already know from physics what the behavior will be like. It will help you to verify whether your answer actually is going the right way. It actually helps a lot in fact, it helps a lot to know the answer beforehand. Here, of course, you cannot know the answer perfectly beforehand. You will not know all the details of it, but you will at least know the behavior at the end of your calculation. You get an expression which gives you a high pass that is wrong. Which acts as a short? That's okay. Maybe I was not very clear. At high frequencies, capacitors act like shorts. So this acts like a short, this also acts like a short. So basically what you have is the R with another R here that's shorted out by a capacitor. Then extremely high frequencies, this capacitor will behave like a zero resistance. So this will be like resistance and a short. Remember, once you're, what else you have to it in parallel to it doesn't really matter because you're going to get a short and you're getting your output here, right? So R and a zero resistance. So how much resistance voltage is dropped across the zero resistance? The answer is none. Both capacitors act as shorts, but this capacitor at least has a resistance connected to it. But this capacitor is just, of course, that happens at very high frequencies. So at very high frequencies, the output is going to go to zero again. At very low frequencies, it's going to go to zero simply because this capacitor is like an open circuit. Okay, both capacitors behave like open circuits, but this capacitor plays the dominant role. Because it's an open circuit, it blocks current from flowing, so no current flows. Now, if no current flows, you might say no current flows, no voltage drop. That's what we did earlier. True, no voltage drop across this R, but also no voltage drop across this R. All the voltage will be dropped across this capacitor. Then, low frequencies. Okay, and then you're going to get this resistance as something through which no current flows, so no voltage drop across it. What I would want to emphasize over and over again is Ohm's law is essentially all you need for most of electronics. Although electronics is very nonlinear, but very often what we do is we approximate it by linear parts anyway. So you end up using Ohm's law much more than you would give it credit for. You would think that when you're dealing with nonlinear devices, you would not use Ohm's law a lot, but you actually use Ohm's law quite a lot. But it's very important to understand exactly what Ohm's law says. Ohm's law doesn't say that the voltage will be large when current is large. It means it says the voltage drop across two ends of an impedance will be large when the current through that impedance is large. That is something you have to actually bear in mind whenever you do calculations or whenever you think of things like this. It's always a voltage drop that you're talking about. Here, the output voltage is a drop across this R. So when zero current flows through the R because the capacitor has blocked everything, there will be no current, no voltage drop across R. So that's a low frequency scenario. The high frequency scenario, this being a short means it shorts out the entire rest of the combination. So although current flows through the short, there is almost no voltage drop because the short offers no impedance. So once again, no output voltage at very high frequency. Okay. Okay, so finally, let me just, this was not a problem sheet, and it's another trivial problem, but still let me just see whether people can get this. So what should it be, low pass or high pass? And
High pass.
high pass means
I mean,
at high
at high
at
frequency,
high
the output will be more.
will be large. That's what high
Yes.
pass means, by the way. How do you conclude that?
So across the capacitor, like if the omega is zero, the impedance is very large. So like the output will be very low. However, for like larger omega, like the impedance
So
will be small.
impedance, so wait a minute, you are saying impedance large and hence output low.
Yes, I mean most of the current will not. I mean the most of the current will flow through the middle R for like low
Yeah.
omega.
Yeah.
However,
Well,
for
I think you should think again. Just think of this.
Sir, I think it's a low pass.
You have a situation like this. Where will most of the drop be? The 1K or the 100K? Okay, there are two different options that I've got. One person has said low pass, the other said high pass. And high pass argument actually is wrong. Okay, that's where you're confused yourself. You're saying this impedance is so high so that most of the current flows through this. I would agree. But remember, once an impedance is high, it doesn't really, because remember, this one and this one are parallel, right? So the voltage drop across this R and the voltage drop across this RC must be the same. And in this RC, almost all the voltage will be dropped across the capacitor, nothing across the R. So basically, voltage drop across this C and this R are exactly the same at omega equal to 0. At omega equal to 0, both C and R drop the same voltage. So would you want to change your answer now? Just think of what happens at very high frequencies. This can't be a pass for the simple reason that at very high frequencies, this is nearly a short. And no matter how much current you drive through a short, the voltage drop across a short is always going to be 0. So at high frequencies, this is definitely going to give you 0 output. The real question is what happens at low frequencies. Does it give you full output, zero partial output, or zero output? So there is actually no doubt here that at high frequency we are going to get something like this. The real question is, will you get something like this or something like this? So low frequencies, could you just figure out, okay, can anybody tell me what exactly VO will be at low frequencies? It's not zero, it's something else. How much is it?
Vi by 2.
Exactly, it's going to be Vi by 2. There are many ways of saying it. One of them is simply that once capacitor is infinite impedance, then this branch is really not there. So you have two resistances, R and R. The voltage will be equally divided between them. So this will be Vi by 2 across the resistor. But if it's Vi by 2 across the resistor, it's also Vi by 2 across this combination. And in this combination, the entire voltage will be dropped across the capacitor. So it's going to be Vi by 2. The other way, perhaps even the simpler way, is use Thevenin's theorem. Use the fact that because you are interested in the voltage here, why don't you treat this as a Theveninized circuit? And there, the open circuit voltage is easily seen to be Vi by 2. And the resistance, by the way, what is R Thevenin for this circuit? How much is it? The easiest way to find out R Thevenin, if you don't have control sources, is simply look in from this pair of terminals. Replace all the sources, in this case Vi by a short, and what is the resistance you see from this side? How much is that?
3R by 2.
Exactly. It's 3R by 2. So basically what this circuit is a simple RC, but an RC with an input voltage of Vi by 2. So the peak value will not, so this will be a low pass, but the peak value will be Vi by 2 and not Vi, as with a single RC. Now also the cutoff frequency. For that you have to use C by 2 R and C, not R and C. So this kind of simple arguments can actually tell you a lot about these circuits without actually having to do a full calculation. Okay. I'm not saying that you should not do a full calculation, but if you have an idea about what the answer will be before you even start out, it will be easy for you to yourself figure out whether you're doing it right or not. If you do a very complicated calculation, in the end you get some answer, maybe completely lost as to what is the right answer. Okay. Now this is a low pass, as several of you have said. It's a low pass simply because if you look at the Thevenin equivalent, it's simply an RC length, nothing else. Okay. So it has to be low pass, nothing else. Okay, I will call it a day today. I will open up the link for the program till Thursday. So you have some time to submit the program. The problem sheet will be there by Wednesday, but that will also have a deadline on next Monday. And once again, if you find the problem sheet long, you can't finish the whole thing, don't worry. You may not be able to finish the whole thing. That's fine. Whatever you can finish, submit that. Okay, so we are done for now.
So, will you take a question?
Yeah, good. Yeah.
So a parallel resonant circuit is a circuit where the L and C are in parallel and the R is in series, right?
L and C are in parallel. If you are using LCR parallel resonance, is that what you're saying?
Yes, that is
This is L, C. That's also called a tank circuit, and you have a resistance like this. Pardon my poor drawing skills, but
so I was just wondering, what would you call a circuit where all L, C, R are in parallel? Because when I first read parallel resonant circuit, I thought like all of them are in parallel.
The
But
trouble with putting all three in parallel, if you ever did that, that's a good question. But you have to understand that a resonant circuit is meant to be resonant in the sense it's supposed to produce a huge output when you have a particular frequency and very low output for other frequencies, right? Now you put everything like this and you're a VI. How much would VO be?
same as Vi.
Exactly. Always, no matter what the frequency is, right? Is that
Yes,
okay?
sir. Yes, sir.
So it will not be a resonant circuit at all. So that's a very nice question to ask, but is putting R, C, and L all three in parallel would not give you a resonant circuit. In fact, the job of the resistance is actually very important. You might say, you might actually think that because at resonance, what happens here is the L and C combination has infinite impedance, right? For remember, the admittances add up for parallel, and so the admittance are 1 by j omega L and j omega C, right? This is the net admittance of this parallel combination. So at a particular frequency, when omega equal to 1 by root LC, these two complex numbers are actually exactly negatives of each other. So you will get an admittance of 0. Or it's reciprocal, the impedance will be infinite. Now, if you have an infinite impedance that blocks the current from flowing, so once again, no current flows here, no drop across the resistance. So entire drop will be across the output. So VO will be equal to VI at this particular frequency. Now, VO being equal to VI at a particular frequency is not a hallmark of resonance. The hallmark of resonance is VO is largest at a particular particular frequency. And when you move away from that frequency, what is going to happen is that the output needs to drop, right? When you move away in both directions, either towards larger frequencies or towards smaller frequencies, the output needs to drop from the maximum value. Now here, when you move away from the resonant frequency, the impedance of this LC tank becomes finite. It's no longer infinite. So it allows current to flow. And once current flows, there's a drop across R, which makes VO go down. Okay. And that's why you need the R in series. Without the R in series, suppose you did not have the R at all, you just had L and C. Even then, VO would always be equal to VI for all frequencies. The job of the R is to bring the current voltage down for other frequencies. So it's not just the resonant frequency where VO becomes equal to VI, where VO by VI is 1. What you want to ensure is that as you move away, the VO by VI ratio drops. And for that, you need the R. By the way, do you need a large R or a small R for a good resonance? If you want a sharp resonance, do you want the resistance to be big or small? Sorry, couldn't hear you. You want the resonance to be sharp, then do you want R to be large or small?
Small, sir.
No. That's exactly the problem with trying to put results from one circuit onto another. You need a small resistance in a series LCR circuit for sharp resonance. In a parallel LCR circuit, as I just said, the job of the R is to bring the voltage down, right? As you move away from the resonance, the voltage has to come down. And if the R is large, it's going to come down more. Simple. It's large R which gives you a good resonance. Small R doesn't. Small R gives you a good resonance for a series LCR circuit. Okay? This is actually critically important because series LCR and parallel LCR have different behavior. In fact, this is the reason why parallel LCR is actually favored over series LCR. When you really want high high quality resonance. Okay, I'm completely out of time today, and I really should not keep you from any further classes you have. So we will discuss this on the next class if you want a further clarification, or it's also in the video. Maybe not right now. The next video will have that, if it's not in this one. Okay, let's call it a day today.